You glance at the UV index on your phone, shrug, and rub on sunscreen like it's just another tiny chore, right up there with charging your battery. Now take pieces of that comfort away. No SPF. No sunglasses. No windows. No car. No roof. No pharmacy aisle. No shade you can count on. You're a Homo sapiens living where the sun hits hard, and your skin is exposed because that's just normal. The sunlight isn't nice weather. It's a daily force that can punish your body for years, and you don't get to tap out and go indoors. That's the twist. Remove modern protections, and sunlight turns into something natural selection can actually measure. So, if sunlight is just nice weather today, why did it become a life or death force that shaped ancient humans' skin color? Because for prehistoric humans, there was no escape plan. Over many generations, skin pigmentation became part of a survival compromise tied to local UV levels. And here's the frame that matters from the start. Skin color was not a race ladder. It was a sunlight map. Across the world, pigmentation patterns track UV geography far more than any supposed ranking of people. Also, this story is mainly about Homo sapiens' skin pigmentation evolution. Ancient humans weren't one single group, and most fossils don't preserve skin color anyway. Once you see sunlight as pressure, sunscreen and indoor life start to look like modern cheat codes, useful for health choices and for rejecting racial myths. So, if the sun was the pressure, what exactly did the body build to deal with it? The sun is straight overhead, and the ground throws the heat back at you. A small band of ancient humans has been moving for hours across an equatorial savanna, tracking game with no shade breaks, no long sleeves, no sunglasses, and definitely no bottle of SPF in a bag. Under light like this, skin isn't just what you look like, it's the surface taking the hit first. So under intense equatorial UV, what trait actually helped ancient humans survive and have healthy children? One answer is more of the body's built-in pigment doing its job. As ultraviolet radiation slams into exposed skin day after day, higher melanin levels help absorb and scatter that UV before it can do as much harm deeper down. Less damage means fewer burned, blistered days that slow you down, fewer infections from broken skin, and fewer long-term hits to the body's cells. And there's a second, more cautious idea folded into the same UV protection model. Intense UV may also threaten folate-related processes that matter for reproduction and early development. Melanin doesn't solve one vitamin problem. It helps lower UV exposure, and that can protect multiple fragile systems at once. This is why the dark equals primitive myth collapses on contact with biology. Darker pigmentation is not an earlier stage of humanity. It's a high-performance adaptation for high UV places, the same logic you're using when you buy sunscreen because a burn isn't just cosmetic. But if more melanin blocks UV, what happens when your group moves to places where UVB is weak for months? You pull a bottle of vitamin D off a shelf and twist the cap like it's just another winter chore, right next to scraping ice off a windshield. Now, imagine you don't have the bottle. You have only what the sun can give you. It's high latitude in winter. The sun sits low, the days are short, and thick clouds can hang around for weeks. A family stays bundled up and sheltered because cold is not a motivational speaker. Bare skin is rare, and the kind of sunlight that matters most here is rarer. UVB is the slice of sunlight your skin can use to start making vitamin D. But at higher latitudes, especially in winter, UVB drops hard. The angle of the sun means less of it gets through the atmosphere, and what's left has fewer chances to reach uncovered skin. So here's the question. Why would lighter pigmentation ever be favored if melanin protects you? Because melanin is also a filter. In places where UVB is scarce, heavy filtering can become its own problem. If too little UVB gets into the skin, vitamin D production can fall, and that can affect bones, immune function, and growth. Smithsonian Human Origins highlights this vitamin D hypothesis as a major explanation for why lighter pigmentation was favored in some low UV regions. That's the trap. What protects you near intense sun can cost you when the sun barely shows up. There isn't one best skin color, only a best compromise for local sunlight, season, and lifestyle. If this is an environmental trade-off, why didn't skin color change instantly when ancient humans migrated? And why doesn't every low UV place end up the same? You drag a pin across a map app and watch the route update in seconds. Ancient humans didn't get rerouting. They moved in steps, over lifetimes, following water, animals, coastlines, and luck. Small groups left Africa into the Middle East, then split and spread into Europe, across Asia, down into Oceania, and much later into the Americas. With every move, the sunlight changed. So did cloud cover, seasons, food, and how much skin stayed covered just to stay warm. When ancient humans moved across the world, why didn't everyone's skin color shift quickly and in the same direction? Because evolution doesn't repaint a person. It shifts populations, slowly, through generations. If a group stayed small, a few random genetic changes could spread just by chance. That's genetic drift, and it can nudge traits in ways that don't match a simple UV equals color chart. Then there's mixing. Groups didn't travel in sealed bubbles. When populations met and had children, gene flow blended histories, pulling skin color traits in multiple directions at once, and culture edited the pressure. A hide cloak, a shaded shelter, a coastal lifestyle, or a diet with more vitamin D could reduce how much sunlight mattered on skin, at least for a while. Not everyone faced the same exposure, even at the same latitude. That's why human skin color evolution looks uneven. Different routes, different ancestors, different mixing, different luck, different timelines. Your own ancestry results can read like that too. Movement and blending, not neat categories. Okay, but can we ever test what prehistoric humans likely looked like? Or is it all guessing from sunlight maps? You sign a consent form, pull on gloves, and watch someone treat a speck of ancient bone like it's a priceless password. A fossil won't keep its skin color. Bone survives, melanin doesn't. So, how do scientists infer ancient skin pigmentation if fossils don't preserve skin color? In the lab, that tiny fragment gets ground down, cleaned, and turned into strings of DNA letters. Those letters can include variants linked to pigmentation, the kind studied in living people today. When enough of those spots are readable, researchers can run a model that says what's more likely and what's less likely. Then comes the moment the public remembers. A face reconstruction appears, confident and human. And the important part is easy to miss, because it's not dramatic. The label matters more than the face. Probability model, not a photo. Cheddar Man is the careful example. He's one Mesolithic person from Britain, whose ancient DNA was analyzed and compared to reference data. Museum materials describe his reconstructed traits as most consistent with darker pigmentation categories and blue eyes. That surprised a lot of people who assumed ancient Europeans were automatically pale. Like, Europe has been the same look forever. But ancient DNA is not a time machine selfie. Genomes can be incomplete or damaged. Skin color is polygenic, shaped by many genes, not one switch. And prediction models lean on present-day datasets, which can bias results toward what's best studied. So, when a headline goes viral, read it like weather forecast odds, not like eyewitness testimony. If one European case can surprise us, what happens when we zoom out globally? Africa, East Asia, the Arctic, Oceania, do they all follow the same genetic script? You zoom a weather app out until the whole planet fits on your screen, and the UV layer turns the world into bands of risk. It feels tidy, like the sun filed everything into neat categories while you're just trying to plan a weekend. Now lay ancient humans' migration routes across that UV map, and you get a tempting rule. Strong UV, darker skin, weak UV, lighter skin. So, if UV matters so much, why doesn't every region end up with the same answer? And why do similar tones show up through different genetics? Because UV is only the pressure. History is the machine. Start with Africa. Genomic studies keep showing that Africa is not one pigmentation category. It holds deep, non-uniform variation shaped across multiple genes and many local histories, because people lived for a very long time in different environments, with different movement and mixture patterns. Then look at Europe and East Asia. Both regions include populations with lighter skin today, but reviews of pigmentation genetics suggest they did not get there by identical routes. Some well-known European-associated variants are less central in East Asia, where other variants play a bigger role. Similar result, partly different toolkits. And then the UV map breaks in cold places near the Arctic coast. Low UV should push hard for lighter skin, but diet can change the math. Marine foods can provide vitamin D, reducing the penalty of lower UVB. Meanwhile, heavy clothing blocks sunlight from reaching skin at all, which can amplify vitamin D risk even when the UV index says, not that bad. So skin color evolution isn't a single global script. It's UV plus ancestry, diet, clothing, and local population history. That's the modern upgrade too. Drop race shortcuts and use a better model environment plus ancestry plus culture without ranking anyone. So after all this complexity, what's the simplest true sentence we can keep? And what myths should we permanently retire? You set your phone on the table, open a UV forecast, and suddenly the planet looks like zones of pressure. The annoying part is realizing your ancestors didn't get to close the app. So why did ancient humans develop different skin colors? And what should we stop saying about it? Picture many human hands, all different tones, resting over that glowing UV map. As the map shifts, it turns into a long timeline. People moving, mixing, changing diets, making clothes, adapting in place for thousands of years. Then, it settles back into the hands. Here's the clean model. Skin color is a local compromise, over a long time, shaped by UV radiation and melanin, plus the need to make enough vitamin D when UVB is weak, plus likely protection of folate-related biology in strong sun. Then real life piles on. Migration, ancestry, genetic mixing, diet, and clothing that can block sunlight completely. That's why it's not a straight story where humans went from dark to light. It's also not a ranking, and it's not something fossils can just show you like a label. Use this filter today. Talk about health in terms of UV and vitamin D risk. Talk about identity as ancestry and history, and shut down anyone using evolution to sell race myths. Skin color records where your people lived under the sun, not where they belong above anyone else. If you like this video, don't forget to like, share, and subscribe to stay tuned for future videos.